What's up, music nerds? I'm back with Chapter 9 of Hermann Helmholtz on the Sensations of Tone. As always, the link to the webbook that I'm reading from is in the description. You can find the entire text of the book there, as well as all the apps that I'm going to show you in this video, so let's get to it. Chapter 9, Deep and Deepest Tones. The question, what is the smallest number of vibrations in a second which can produce the sensation of a musical tone, has hitherto received very contradictory replies. The estimates of different observers fluctuate between 8 and about 30. Let's take a listen. You're definitely going to need headphones for this. Whoa, that's 16 and I really can't hear it. 8? I got nothing. Let's try something around 30. Definitely I can hear that. At about 25 is where it stops sounding like a musical tone and more like a wubba wubba. And that's where I lose it altogether. 12.98. When experimenting with these really deep tones, the vibration of the air has to be much greater than it is for higher tones in order for it to create a similar impression on the ear. And Helmholtz proves this by using the exact same amount of force on the bellows of his siren to produce a high pitch and a low pitch, and the sensation is much more powerful for the high pitch than it is for the low pitch, even though he's using the exact same amount of force mechanically to create the sound. It follows that in compound tones of great depth, the upper partial tones may be superior to the prime in strength. This is readily proved on my double siren, because by means of beats, it is easy to determine whether any partial tone which we hear is the prime or the second or third partial tone of the compound under examination. We can do a virtual version of this experiment with these two keyboards. The bottom keyboard is 4 Hz higher than the top, so if we play 2 notes in unison, we should hear 4 beats per second. Now let's change to a square shape, which gives us more upper partials. Oh, this is a good time to show you guys this tool down here on this pull-out menu. The box on the left here is going to show us the waveform of whatever sound is playing. The box in the middle is going to show us the spectrum analysis. So let's start with a sine wave. Here we can see the sine wave. And on the spectrum analysis, we don't have frequencies on the graph, but we can see that there's 1 spike for the prime tone. Now, if we change to a square, that's what it looks like. And you can see we have many more spikes on our spectrum analysis for all of the upper partial tones. There's what a sawtooth looks like. And a triangle. Now, back to the experiment. Let's go with a square wave. And up here, I can still hear 4 beats. But down here, I'm hearing 8. Which means that I'm hearing the second partial tone more than I'm hearing the prime tone. The conclusions Helmholtz comes to from these experiments: the first audible tones produced make 12 beats for each revolution of the handle, the number of puffs being from 36 to 40 in the second. For tones from 40 to 80 puffs, each revolution of the handle gives 8 beats, and it is not until we have 80 puffs in a second that we hear the 4 beats of the prime tones. I'm going to go back to our first keyboard, which gave us frequency. C right here is close to 80, and an octave below is close to 40. So mess around between these two octaves. Use different shaped waves. Count the number of beats you're hearing and tell me your results in the comments. All right, so why does this matter? Well, in order to discover the limit of deepest tones, it is necessary not only to produce very violent agitations in the air, but to give these the form of simple pendular vibrations. Until this last condition is fulfilled, we cannot possibly say whether the deep tones we hear belong to the prime tone or to an upper partial tone of the motion of the air. Helmholtz uses wide-stopped organ pipes, strings which are weighted in the middle, and weighted tuning forks to achieve these low tones with very weak upper partials. And he concludes that nerve fibers begin as early as 24 to 28 vibrations per second, but aren't able to discern a definite pitch until around 40 vibrations, and it's not until 110 to 117 that we stop perceiving distinctive pulses of air and start perceiving a continuous pitch. You can go back up to that first keyboard and see if you agree with those numbers. At this point in the chapter, we shift slightly to talk about cutting, snarling, or braying tones. In previous chapters, we've determined that this quality of tone is due to a large number of distinct upper partial tones. But more specifically, it is the beats produced by these upper partials. If the 15th and 16th partials of a compound tone are still audible, they form the interval of a semitone and naturally produce the cutting beats of this dissonance. It is really the beats of these tones which cause the roughness of the whole compound tone. Let's go back to this keyboard here and pull out our menu again. There's our sine wave, triangle, square, and sawtooth. Of all four shapes, the sawtooth has the most and loudest upper partials, and I would characterize it as the most cutting of those four sounds. But, of course, our ears have an upper limit as well as a lower limit. So in the case of high pitches, the upper partials, which are close together enough to cause that beating, are so high that they're inaudible, which is why we find soprano voices so pleasing to the ear. And that brings us to the end of chapter 9. If you've made it to the end of this video, then you've got to go to sensationsofTone.com and try out the experiment in this chapter and leave your results in the comments below. And of course, subscribe to the channel so that you don't miss me next week with chapter 10. I'll see you then. Bye!